Okay, so let's get started. So I stopped just short of the fine spectral expansion. So let me do the fine spectral expansion for, let me write the terms involved first, and then two other computations for SL2, and then go with the invariant trace formula. So this is the fine spectral expansion. So if you have any F, so here the F is in the Heck algebra of G, which is the space of bi K invariant functions in C infinity C G A. So if you have this, then the and chi in X, the formula for J chi is given by this. It's a sum over the standard Levy subgroups of pi unitary representations of MA1 of the sum over regular elements in the while group of there are two terms here. So one is the size of the while groups, the ratio of this, times the determinant of so inverse of this, times there is an integral IA L star mod IA G star of the trace. So this is the smooth function for the intertwining operator. This is a unitary operator MPS 0, and finally you have the IP chi pi lambda F d lambda. So this is the expression for this J chi, and when L equal to G, this integral disappears, and in that case Arthur calls this as the discrete part of the trace formula when you sum over all chi's. So note L equal to G implies IA L star IA G star is trivial. So this is called the discrete part of the trace formula. Okay, and let us write all the terms explicitly for SL2. So when G is SL2, there are only two choices of Levy subgroups, M0 and G. So there are three cases here. One is that M and L both are equal to G, in which case, so I haven't defined what this WLM regular is. WLM, so let me write WLM is nothing but inside WL, you look at the isomorphisms which take AM to itself. This is this set, while set, and the regular elements are precisely those for which this makes sense. This is well defined. Okay, so this is the elements here for which this determinant is non-zero, so you can invert it. Now in this case, I want to know what this WLM is. So WLM in this case will be WG AG AG, and AG is just the trivial. So this is just one, and this is a regular element because this is the zero. I mean, it's a zero map on the zero vector space, so its determinant is 1. So there is a contribution for this. The contribution from this is given by a sum over pi cuspidal automorphic representations of the multiplicity is 1, and you have the trace, the mg, so everything is g here, so L is g, so this is 1, this p is g, this is 1, so I'm left only with this, so I, g, chi, pi, lambda, f. Lambda is 0, so lambda is 0, and in Ig there is no induction, so there's just, so this is nothing but trace of pi of f, and multiplicity is 1 here. So this is the one term, and then the second term is when m is the minimal Levy and L is g. So in this case also this integral will disappear. So if I look at WL m, then WG, so there are WG, A0, and this is just WG. So if you look at the two elements here, then you want to look at this map. LM is A0, and in A0 the two elements, trivial and the long while group element. The trivial element -1 will give determinant 0, so that is not regular. But the long element is -1, so -1 is -2. So that one you have some contribution. So WL M regular is the long element W0, and the contribution from that element is so pi is in pi unitary representation of M0A 1. You have half, so half here and half here, that gives 1 over 4 trace of M0, W0, 0, I0, chi, pi, 0f. Yeah, so this is the contribution. And finally, when both are M0, then you get an integral. So W L M is W M0 A0 A0, and kind of by definition this is identity and this is regular. So the contribution here is a half integral of the trace M0 P0 lambda M P0 of 1, 0 I P0 chi pi lambda f d lambda, and this is the identity map, so you can throw it away. And so and this is the logarithmic derivative, so you can write this as m lambda inverse m prime lambda. Yeah, so this is the contribution here, and so these are the three contributions. Yeah, I think here. Oh yeah, okay. Yeah. Yeah, so trace of, yeah. The non-cuspidal discrete is the trivial representation. Because determinant is 1, so there is no character and so on. Yeah. Okay, so I will stop the discussion of the spectral expansion. And before I go to the invariant trace formula, I will give some relation of this with beyond endoscopy. So there's some short note that I have. Yeah. Levy of P. P is M. Where is it? Yeah, here, for example. Here, P of M. Yeah. Okay. Okay, so this is some small section, relation with beyond endoscopy. So let G be SL2, but you don't have to take this. You can take any G. And let R be the representation of SL2C inside GLV. So it's a representation of the L group. Now for every prime P, so fix for P prime. Yeah. So let me take G to be PG. Okay. It doesn't matter actually. Nothing matters, of course. But no, I mean, sorry, I should not say that. What I want to say is, a particular choice of G doesn't matter in this case. Everything works for a connected deductive group. That's what I meant. Yeah. So let's write G. Because Satake isomer, what I'm going to do, everything is general. So LG and G is a connected deductive group over Q. With the representation of LG. Now for a fixed prime P, you have this unique by. So let me write. So there exists a unique by. Now here a little bit. I want G to be defined over Z. Some special thing I will assume, because I want G of ZP by G of ZP invariant, and the maximal compact subgroup here at P is G of ZP. So there exists a unique by ZP invariant function phi, but it is indexed with P, the representation R, and a complex parameter S, defined on G of QP. It is bi-invariant and it satisfies the property such that trace of pi p phi p r s is equal to the LP, the local L factor at S pi p r for all pi p unramified, irreducible, admissible, representation of G of QP. So this test function gives you L factor on the nose. So if this is the condition, and now at the Archimedean place, I will choose some function, then come up with a test function on the adelic points and plug it in the trace formula. Sorry. Yeah, so this, and then for V equals infinity, let V infinity be a smooth L1 function such that its derivatives are also L1. So this is some class of test functions. And then you form the function, you combine everything and write phi rs as phi infinity times product over p, phi p rs. If you do this, then it's a function on, this is a function on GA of not compact, not necessarily of compact support. Now so per se you cannot apply it in the trace formula as a test function, but there is a result of a recent result that says you can. So the theorem, this is by Finis, Lapid, Muller, spectral side, and Finis and Lapid on the geometric side, that the geometric and spectral sides of the trace formula converge absolutely for such test functions, In particular, the spectral side is absolutely convergent. For F in the Heck algebra. So this was not known to Arthur. I mean, Arthur could not use this, and so he had to juggle. Like he had to do some balancing. He had to cut out by some infinitesimal character bound and something. So this theorem says that the trace formula, both distributions converge, and you can use these functions in the trace formula, which give you the L factor on the nose. And similar result for the twisted trace formula is a work by yours truly. Yeah. So I will apply this function to the trace formula at the spectral side. So if I have a discrete automorphic representation in the discrete spectrum, what happens if I apply the test function to the spectral side? What is the contribution of that pi in the discrete spectrum? Yeah, S has to be large enough. Thank you. Yeah, so suppose pi is tensor pi v, let B, and automorphic representation in the discrete spectrum. Then the contribution is non-zero. Its contribution to the spectral side is non-zero precisely when pi is unramified at all finite places. I mean, you can play with this. You can choose some finite set S and you can do these things. But for the easy case, let's say at every place you choose this as a test function. then pi needs to be unramified. And if so, if this happens, if so, the contribution is L infinity S pi infinity R. So yeah, so this, and so my understanding of the beyond endoscopy is, yeah, times the infinity part. So trace pi infinity, yeah, sure, yeah, okay. So I'm saying that pi is unramified, otherwise it is 0, the contribution is 0 for this test function. Yeah, and then if it is unramified at all p outside infinity, then the contribution is this. In the spectral side, to the spectral side. So you have a J spec, right, of this V R S. This is something. You don't like it? Yes, I'm taking this function. No, it is pi. So pi's are varying, right? So you're catching only the ones that are unramified at infinity. The sum, when you take sum over pi, then whatever you get is contribution. It's only those kinds of pi's. That's what I'm saying. Yeah, maybe there is multiplicity. Yeah, that's right. Yeah. M pi something. Yeah. Okay. Thanks. So my understanding of beyond endoscopy is that you try to adopt the method of Godemont-Jacquet. There is a lot of work involved, like define the monoid and the Fourier transform and Poisson summation, and get the L function somehow, and then you weight the trace formula by that L function and get an R trace formula, and for a particular R, and then you are able to you are hoping that you will compare the R trace formulas and get some information about the spectra. That is some idea here. So okay, so I will stop this discussion and go to the invariant trace formula now. Okay. All right. So we have, so this is the invariant. Now, so we have an expression that looks like this, O in O, J O F. J chi F, and this holds for F in the Hecke algebra of G. Now, if you have a so for y in GA, the function Fy, which is defined as Fy of x, is conjugation by y, need not be in the Hecke algebra. It need not be k finite. And so you define invariant, a distribution to be invariant. There's a different definition. Define a distribution a distribution is invariant if for fixed x, fixed function h in the Hecke algebra, if you convolve on the left and right, you get the same value. You have that a distribution. Let me name this distribution as J. Then I need that J of f is the same as J of h convolution f is the same as J of f convolution h for all f in the Hecke algebra. Okay. So if it has if it assumes same values at these places, then you call it an invariant distribution. And for SL2, this, first of all, this agrees with the previous definition, and Arthur gives formulas for, the previous formulas hold with a similar modification. What I'm saying is, you had J of Fy, and so if you can have J of F star H, and some similar formulas will hold for these as well. Now for G's SL2, the terms with M equal to G are already invariant. And the terms with M equals M naught are not invariant. So we need to fix these. Now what Arthur does is, for this expansion, he modifies the geometric expansion as well as the spectral expansion so that the terms are indexed by Levy subgroups. And then you can see explicitly the contribution of those Levy subgroups. So here are the two expansions. So if you, for the geometric expansion, recall that from yesterday's that for a given coarse conjugacy class, you had a set SO such that if you S contains SO, then the expression for JOF looks like this. It's a sum over Levy, standard Levy subgroups of W0M. He defines MS equivalence classes, and for gamma here you have AM gamma S, JM F gamma or gamma F. And we defined these invariant orbital integrals, weighted orbital integrals yesterday. So we have this. And if you want to combine this for all O's, then he writes, so given a F in the Hecke algebra, there's a finite set of places outside which, where F is supported. So there is an S such that you can think of F as sitting inside G of Fs. So you can write this J of F in general as a limit over S of the sum M in L of all these above, same as above. So this is the sum over L, M in L, and now I will do the same thing for the spectral side. I will write it as a sum over standard Levy subgroups. So when Arthur wrote this invariant trace formula paper, he did not know that the spectral side converges. So he had to do some modifications. And I will just stick with those modifications, but they don't necessarily, we don't have to do that now because we know that the spectral side converges absolutely. So he defines certain objects. So nu pi is the infinitesimal character of pi, and you take the imaginary part of that and take the norm, then it has to equal t, and some t is greater than or equal to 0. So you are fixed, you want finite, Arthur wants to impose some finiteness condition because he cannot sum over the all spectrum. He doesn't know that it's not converging, it converges or not. So there is some restriction. So t means the infinitesimal character, imaginary part, norm has to be equal to t. And then similarly you define pi t disk G as irreducible constituents of representations induced from sigma on the Levy twisted by lambda all the way up to G, such that M is a Levy subgroup, sigma is in pi t unit MA1, and lambda is in IAM star mod IAG star, such that AM disk sigma is non-zero, and there exists an S in WG AM regular, such that S of sigma equal to sigma lambda equal to sigma lambda. So this is one set, and there is something more. So pi tg is the set of all pi lambda g. Pi is in pi t disk of M. Lambda is in IAM star. And this set has a measure. And finally, you define pi g t to be the union over t less than equal to t of pi tg. So these sets he defines because he wants some finiteness conditions. So it is like fixing a level or something. So if this happens, then the spectral expansion, you can write this as the following. So it's a limit as t goes to infinity. So more and more you're enlarging the spectrum of the sum over levies. Pi mt, am pi, jm of pi f, d pi. Now I have to tell you what jm pi is. So jm pi is given by the following. So it's the integral of jm pi lambda f d lambda, and lambda is in I A m star, and Jm pi lambda f is the trace of R m pi lambda p I p pi lambda f. So p is in P of m. Now so you have the intertwining operators. You know that they converge, and they have another important property of the intertwining operators is that they can be normalized. So the functional equation that holds for not all the time, but depending on the length of the Weyl group elements and so on, it holds in general when you normalize the intertwining operators. Now, when you normalize the intertwining operators, the normalizing factors, which are the which come from L functions, they are also they also form a GM family, and so this R m pi lambda is the smooth function corresponding to the product GM family of the product of the normalizing factor with the normalized non-normalized intertwining operator. So it's something to do with this. So this is that term here, and so one slight thing is there is an f tilde here, and f tilde is any function on GA which restricts to f on GA1. So f is initially defined on GA1. You take any function which is defined on the larger GA, and you integrate that. It doesn't matter which function you choose. So if you do this, now I will write the trace formula in this fashion, like this expansion and this expansion for SL2. So explicitly for SL2, so fix an x, fix an f in C infinity C GFS 1 or QS. So S is a finite set of places, so you fix those finite set of places, and then JF, the term for the Levy subgroup is gamma in GQ, GS, AG gamma, JG gamma F. This is the contribution from the G. And now I have a contribution from the Levy M naught. So this one is already invariant, and the Levy contribution is the following. M naught Q, M naught S. So again, this is M naught S equivalence classes, but actually there is no M naught S. So this is just M naught of CS of A M naught gamma J M naught gamma F. And explicitly you can, this is nothing but the volume of M of ZS mod M of QS1. Similarly, I will write the spectral expansion. It will have two terms, one for G and one for M naught. So this is pi in pi G, AG pi. This is nothing but 1. And the JG, JG pi F. So pi is cuspidal automorphic representation in the discrete spectrum, so trivial also. So this is just the trace of pi of F. Plus the Levy contribution is half pi in pi M naught A M naught pi. This is 1, and J M naught pi F d pi. So if you look at this, these terms are invariant already, and then these terms are not invariant. These distributions, I mean the distribution this and this. So Arthur has to modify these distributions to convert this trace formula into a invariant trace formula. So I will briefly explain what is going on there. And since our M0 is abelian, things are simplified, and actually it's a Fourier inversion formula there. So I will first write the theorem and then explain what is going on. So the theorem is that you have this invariant distributions. That is a theorem. So for f in the Hecke algebra, there are invariant distributions. I m gamma f and I m phi f defined inductively so that the geometric expansion which is a limit over S of some standard Levy subgroups, the same thing. So this equals the spectral expansion. Oh, sorry, not J, I. Otherwise, what is there? IMF equals the spectral expansion. And so here it is the limit over T. Actually, we don't need now the limit over T, but I will just keep it. M in L integral, so mod W0 M pi MT A M pi I M pi F d pi. So this is the theorem. Arthur says there exist invariant distributions I m and I m gamma and I m pi, so that this spectral side equals geometric side. Now the way he constructs this I m is inductive. So you assume for smaller Levy subgroups, and then so I will write another theorem that says how this is obtained from what is known as distribution supported on characters. Then I will explain what the distribution supported on character means, and then show how these terms can be converted into the, I mean, what is the contribution of these terms to the invariant trace formula. No, there is a slight modification. There is a slight modification. That's a good question. Explicitly there is a formula that gives Im and Jm, and for G they agree. So Im G equal to Jm G. So the main part of that theorem is the following statement that Arthur shows. So Arthur shows there exist invariant distributions supported on characters. I will tell what that means. Im gamma f equals Jm gamma f minus L in L m L not equal to G I L m hat gamma phi L f So HAC is some formal thing that you cannot work with the Hecke algebra, so he increases, he takes some limit and defines this space. And similarly, and something similar holds for the spectral side. So Im phi x f equals Jm phi x f minus the contribution of smaller Levy subgroups. Sorry, this is vector side. So pi x L of f, and here pi is pi m qs, x is in the AMS, and f is in the Hecke algebra, some HAC G of qs. And what does supported on characters means? So it means that there is a map. So first of all, before that, if you take M to be G, then you get Im equal to Jm in both the cases. And if you take M to be the minimal Levy of SL2, then you get, there's only one term here, L equals M naught. So I want to know what this I M naught is in both the cases. And so let me define what it means for a distribution to be supported on a character. So you have this HGQS, which is the Hecke algebra. From here you have a map into IGQS, which you can think of as complex valued functions on the tempered spectrum of GQS. And our M naught, we want to apply this for G equal to M naught, and that in that case it is abelian. So this is C valued functions on pi temp GQS. So it is abelian, so you can have the full dual spectrum. You don't have to restrict to the tempered spectrum. And so if you have a distribution here, so this map is F going to Fg. So Fg of pi, for example. And if you have a distribution I, if Fg is 0, then I of f has to be 0. So what I'm saying is define I to be supported on characters if Fg equals 0 implies I of f is 0. So if this happens, then you get a natural map here denoted by I hat. And I hat you define is defined as the invariant Fourier transform. Invariant Fourier transform of f of I. Now, in the case of our minimal Levy, which is abelian, this will turn out very nice. This usual Fourier transform of I. Okay. In the case of SL2, I want to know what this term I M naught is. I will just for G equal to SL2, so the term I M naught hat of gamma phi M naught of F equals, so integral over pi unitary of M naught QS 1, and this is the same as pi tempered, pi of gamma inverse Jm pi f d pi. So this is actually the Fourier transform, the Fourier inversion formula. For the abelian group M naught. Okay, I think I will stop here. Thank you. Oh, no, reasonable, see, sorry, what? No, it's not subjective. Sorry, what is the question? You mean this arrow? Yeah. Okay, so Tasho will continue with the stabilization of SL2 maybe in a while. Yeah. Yeah, you can use it.
Okay. Yeah, I just use that. Fine. So I guess we come to the end of our first week of activities, and maybe we should take this chance to thank the the lecturers who have been giving the courses this week. So Abhishek Parab, Hiraku Atobe, Lei Zhang, and I guess myself. Okay. So thanks. Okay, I know that some of you are just here for 1 week and will be going back over the weekend. So enjoy the rest of your stay in Singapore and wish you a safe trip back. Also, we will have a very long weekend, right? So just make a few announcements about that. So I think that over this period, so of course on Christmas Day is a public holiday here, so the institute will be closed. So I think there's no point coming here for you, because I know some of you have offices here, but I'm not sure if you could get into your office. But on Monday, it should be fine. Okay. However, during this, Monday only half a day. And also during this period, even on Monday, I think, if you're staying around on campus and you're relying on the internal shuttle bus, they will be running on some holiday schedule, which means that they are still running, but maybe less frequent. Okay, I don't actually know what the schedule is. Usually more than half an hour wait in between buses. Okay, so if it's a walkable distance, maybe you want to walk. Okay. On Christmas Day, however, of course, the university is closed, but outside everything else should be open. Public transport runs as usual. Supermarkets are open as usual. Malls and all kind of things I think are all normal. Right? I think even on public holidays here. If anyone feel they for if you are religious and would like to go to church service on Christmas Day and so on, you can let me know. Okay, I can point you somewhere. You're welcome to attend the church that I attend, for example. And also, when we come back on the 26th, which is a Wednesday, there's a change of schedule. I guess you received the email from the secretaries. So instead of having courses, so Hiraku and course and my course were finished. Okay, so instead we will have 2 seminar talks on Wednesday afternoon by Tony Feng and Masao Oi. Right? Okay. I think just 2 seminar talks on Wednesday afternoon. So morning is I think Ray Julian is going to give a continuation of the lectures on Braverman-Kashtan approach to L functions. Okay, so enjoy the super long weekend. We work 4 days, we rest 4 days. That's the way to go. Okay, thank you.
Wish everybody a Merry Christmas.
Yeah, Merry Christmas.